All right, let's dive into some serious AI research. Ready? We're talking transformers today.
Oh, you mean like the things behind ChatGPT? The stuff that generates that crazy good text that sounds like a person wrote it?
Exactly. But this research, this takes it way further, like giving these transformers a chain of thought.
A chain of thought.
Yeah, you could almost imagine it like a mental scratch pad they use to think things through, step by step.
And
And we've got some sources to unpack, excerpts from a pretty dense technical paper, and then some helpful study guides that break down the complexity a bit.
you know what I find fascinating is this isn't just about making the text they produce sound more human.
Oh, okay.
It's about actually changing what these models can do on a fundamental level, their capabilities.
So you're saying this isn't just like writing a better poem or something?
No, no, not at all. Think of it this way. Standard transformers, they're amazing at certain things, like predicting the next word in a sentence.
Yeah, yeah.
But when it comes to tasks that involve a sequence of logical steps, that's where they hit a wall.
So something like writing a computer program.
Exactly. Imagine trying to solve a Sudoku puzzle, right? You have to remember the numbers you've already filled in.
Right.
Standard transformers, they kind of lack that memory. They can't easily keep track of those previous steps.
So it limits how well they can actually like reason through something.
Exactly. That's the bottleneck.
Okay, so how does this whole chain of thought thing, how does that come in to fix this?
Well, it's like imagine giving them a way to jot down their thoughts as they're working through a problem.
Oh, interesting.
Instead of jumping to the answer, they can go step by step.
Oh,
And
right.
that dramatically changes what they're capable of.
But how big of a difference are we talking about? I mean, is this just a slight improvement or is this like a whole new level of AI?
Now that's where it gets really interesting. The paper, it breaks down the power of these transformers into three what they call regimes.
Regimes.
Yeah, based on the number of steps they take in their chain of thought.
Okay, so like levels of thinking.
You got it. First, you have your transformers with no steps. Basically, the standard models we see now, pretty limited reasoning ability.
The basic ones, right?
Right. Then you give them a few steps to work with.
Okay.
Things start to improve, but they still struggle with certain problems, like figuring out if 2 points in a network are connected. It's like they're still getting lost in maze because they don't have enough steps to map out the whole path.
Ah, so they need more than just a few steps to really unlock their full potential.
Exactly. And this is where it gets mind-blowing. When you give them a linear number of steps,
Linear.
meaning the number of steps grows proportionally with the input size, suddenly they can simulate automata.
Automata. Now, those are like theoretical machines, right, that can perform computations.
Exactly. And the fact that transformers can now simulate them with this chain of thought, it's
Wow.
a huge jump. It shows they're capable of way more complex reasoning than we thought.
So how is that even possible? I mean, how do these transformers manage to keep track of all these steps doing these computations?
Well, that's where the researchers introduced a clever trick. They call it the layer norm hash.
Okay, layer norm hash, what is that? Like some kind of magic. And how does that even work with this whole chain of thought thing?
Okay, so think about it like this. You know how programming languages have rules, right?
Yeah, the grammar and all that.
Right. So formal languages are kind of similar, but for defining what computers can actually compute.
Okay.
And this research uses formal languages to try to figure out like what transformers with this whole chain of thought thing can actually do.
So instead of grammar for us, it's grammar for what computers can do.
Yeah, exactly. And the paper specifically dives into this type of transformer called a decoder-only transformer.
Decoder only. So does that mean it can't listen anymore or what?
It can still process input, but it's mainly designed for generating text one piece at a time based on what it's already seen.
Oh, I see.
Kind of like, writing a story where each word you choose depends on the words you wrote before.
Yeah. Yeah, it's still building on what came before.
Right, exactly. And with this chain of thought thing, the process goes like this. It reads the input, then it generates a sequence of intermediate tokens, like it's thinking out loud.
Oh, interesting.
And finally, it uses all of that to produce the final output.
So it's like showing its work as it goes.
Exactly. Yeah. So remember those three regimes of steps we talked
Oh,
about?
yeah.
Well,
Yeah.
the paper defines those formally using something called big O notation.
Big O notation. Is that going to make my head spin?
No, no, it's actually simpler than it sounds. It's just a way to describe how the number of steps grows as the input gets bigger.
Okay.
So logarithmic steps, that means the number of steps grows really slowly,
Mhm.
while linear steps mean they grow proportionally to the size of the input.
Got it. So it's a way of measuring how much thinking the transformer is actually doing.
Exactly. And here's the thing, transformers with different numbers of steps, they actually fall into different complexity classes.
Complexity classes. Now, is this like a ranking system for AI or something?
Kind of, yeah. It's a way to group problems together based on how hard they are for a computer to solve.
Okay.
Problems in the same class, they require a similar amount of computing power.
I got it.
So yeah, this is where those regimes come in. Transformers with OO steps, they're stuck with problems in a class called TC0.
TC. Oh, our listeners got something to share. Let's hear it.
Before we dive into the TC0, can we explain the definition of the layer normal hash?
Before we dive into the complexity classes, I think it's important to remember TC0.
TC0.
Yeah, those are solvable by pretty simple circuits.
Oh, okay.
Like you might have seen in like a basic electronics class.
So the beginner level problems.
Exactly. But then add a logarithmic number of steps.
Okay.
Suddenly they bump up to the complexity class L.
Okay.
Those are
And the
problems
Bosch
that can
Center
be
for
solved
AI.
with limited memory.
And I'm
Mhm.
David
They're
Duvenant,
getting
and
more
I'm at the University
powerful,
of
but
Toronto
still
and the
not
Vector
super
Institute.
powered yet.
Right.
But now
And
here's
I'm
where
Matt
those
Johnson
linear
from
steps
Google
come in,
Brain.
the mind-blowing ones.
Linear.
With linear steps, they can
All
simulate
right, and we're going to
automata.
talk today
Wait, so now our
about
transformers are
deep
graduating
implicit
from basic
layers,
circuits
neural
to
ODEs,
like
equilibrium
simulating
models,
complex machines.
and beyond.
Yeah.
So
That's
to
a
start
big jump.
off,
It is, and that
we're
means
gonna
they
ask the
can handle
question,
much more sophisticated
what do we want to
tasks.
do with deep
Wow.
learning?
Automata, they're all about
So if you're
recognizing
using deep learning,
patterns
you're
in
probably
sequences,
thinking
which is a
about some
core
of like the
concept in
classical
computer
applications
science.
of deep learning. So there are things like
So now they're not just predicting the next word, they're actually
classification, semantic
analyzing
segmentation,
complex patterns.
language
So they're
modeling,
moving
generative
beyond
models.
just like the
These are
surface
domains that
level
have been sort
stuff.
of
Exactly.
major
But even with
breakthroughs
linear
that have
steps, there are
happened
still
due to
limits.
deep
Oh.
learning.
They're kind of stuck
And we all
between
sort of are very
simpler,
aware of some of
regular
these.
languages and the more complex, context-sensitive languages.
Okay.
It's like there's this hierarchy of language complexity.
So even with all those steps, they're still bound by the rules of these language classes.
Right. But the paper takes it even further with polynomial steps,
Oh?
which is a huge number of steps. The transformers become equivalent to the class P.
P. What's so special about P?
P stands for polynomial-time, and it basically covers this massive range of problems that we consider solvable by computers in a reasonable amount of time.
Okay.
Things like sorting data, searching databases, even playing chess.
So with enough steps, transformers could be as powerful as like our regular computers in terms of the problems they can solve?
Theoretically, yeah, but there's a catch. Running a transformer with that many steps, it would take an insane amount of computing power.
Wow.
Not practical yet.
So it's like we have the blueprint for a super fast car, but we don't have the engine to make it run.
Exactly. A perfect analogy. And all of this, it hinges on that layer norm hash thing we mentioned earlier.
Right. The memory trick.
Yeah.
Remind me how that works again, and why is it so crucial for this whole process?
Well, remember how standard transformers have a hard time remembering earlier steps in their thought process?
Yeah.
The layer norm hash, that fixes it.
So it's like giving them like perfect recall.
Precisely. It lets them instantly grab information from any previous step, no matter how many steps there are.
Wow.
And that's essential for simulating those automata and even more complex machines like Turing machines.
So it's not just about having a long chain of thought. It's about being able to access any part of that chain instantly.
Exactly. The layer norm hash is like the glue that holds the whole thing together.
Okay.
Makes these incredible computations possible. It's really elegant with huge implications for the future of AI.
This is so cool. But I got to ask, we've been deep in the theory here, but where does this actually lead us in the real world?
Yes, this is what makes this research exciting.
What are the practical applications of all this mind-blowing research?
Well, I think that's what makes this research so exciting, you know? It's not just theoretical, it could really change things.
Yeah, for sure. So where do you see this going? What applications are you most excited about?
Well, natural language processing, that's a huge one. Think chatbots, translation tools, all of that.
Right.
With chain of thought, we could see language models that don't just sound human, they actually reason and understand things on a deeper level.
So instead of just spitting out grammatically correct sentences, they could actually like follow a logical argument.
Exactly. Imagine asking your voice assistant to plan a complex trip, factoring in all your preferences. Or having a chatbot that truly understands your needs and gives helpful advice.
That would be incredible. No more scrolling through endless travel sites or getting stuck in those chatbot loops. But it sounds like this goes beyond just like language stuff, right?
Oh, absolutely. Robotics is another field that could be completely transformed.
How so?
Imagine robots that can not only perform tasks, but they can plan and reason through complex situations.
Okay, now we're talking robots that can think for themselves. That's both exciting and a little scary, to be honest.
I get it. But think about the possibilities. Robots with chain of thought, they could handle tasks that need a lot of adaptability, problem solving,
Right.
like assembling intricate objects or navigating unfamiliar environments.
So we're not just talking about robots that follow pre-programmed instructions.
Nope, these could learn and adapt on the fly.
Wow. So think like robots helping in dangerous jobs like disaster relief or space exploration, right? Or even performing delicate surgeries.
Exactly.
Wow, those are some serious applications. And it doesn't even stop there, does it? What about like scientific discovery?
Exactly. Scientific discovery is next level potential.
Could chain of thought help us unlock new knowledge?
Oh, absolutely. Imagine using these powerful transformers to analyze huge data sets in astronomy, genomics, climate science. They could help us uncover patterns and connections that we as humans would just miss.
So AI wouldn't just be a tool for scientists, it'd be like a partner in the discovery process.
Exactly. Helping generate hypotheses, design experiments, even interpret results could really accelerate scientific progress.
This is all incredibly exciting, but with any powerful technology, there are always ethical considerations.
Always.
How do we make sure these advances in AI are used responsibly, for the benefit of humanity?
That's such a crucial point. We have to be so mindful of potential biases in these models,
Hmm.
make sure they're developed and used fairly. We need to talk about the potential impact on society, involve experts from different fields in shaping how it's developed.
So it's not just about the technical stuff, it's about the social and ethical implications too.
Exactly. We have to approach this responsibly and make sure these tools are used to create a better future for everyone.
Well, I have to say, this deep dive has been quite the journey.
Definitely.
We've gone from like the nuts and bolts of how chain of thought works to imagining a future where AI is changing industries and pushing the boundaries of science.
It really shows how fast AI is evolving, doesn't it?
And for our listeners, remember, this is just the beginning. There's so much more to explore in the world of AI.
Stay curious, keep learning, and who knows, maybe you'll be the one making the next big breakthrough in this exciting field.
Thanks for joining us on this deep dive, and until next time, keep exploring. It's a wrap.
Yeah, until next time.